A comprehensive overview of atmospheric and spaceflight operation. The boundary between Earth's atmosphere and outer space is generally set at 100 kilometers above sea level. In this region and beyond, spacecraft experience microgravity, a state of very low acceleration, similar to weightlessness, though small forces still exist. Earth's lower atmosphere is made mostly of nitrogen, 78%, and oxygen, 21%, with small amounts of argon and trace gases like water vapor and carbon dioxide. Even though greenhouse gases are present in tiny quantities, they are important because they influence the planet's climate. Temperature in the atmosphere changes with altitude. At the surface, the average is about 15 degrees Celsius, 288 K. As you go higher into the mesosphere, around 50 kilometers, it gets colder. Above about 80 to 90 kilometer, temperatures rise again in the thermosphere because oxygen and nitrogen atoms become ionized by solar radiation. Microgravity happens when an object is in free fall, such as a spacecraft orbiting Earth. In perfect free fall, weightlessness would be total, but in reality, small disturbances prevent this. When changing orbits, spacecraft often use a Hohmann transfer, a method to move between two circular orbits efficiently. This involves applying a sudden change in velocity, delta V, at the right point in the orbit. Adding speed in the direction of motion changes the path into a larger, elliptical orbit. This increases both kinetic and total orbital energy, effectively raising the spacecraft's average altitude. Eventually, another delta V is applied to make the new orbit circular again. In many space missions, a spacecraft on the ground, the chaser, launches to rendezvous with another already in orbit, the target, using careful maneuvers based on these orbital mechanics principles. Introduction. Earth's atmosphere is made mainly of nitrogen, 78%, and oxygen, 21%, with small amounts of argon and trace gases like water vapor and carbon dioxide, which, despite their low concentration, play an important role in regulating climate. The atmosphere is divided into layers: troposphere, stratosphere, mesosphere, and thermosphere, with boundaries like the tropopause, 9 to 17 km, and stratopause, 50 km. The edge of space is usually set at 100 km altitude. In low Earth orbit, LEO, spacecraft experience microgravity, a near-weightless environment, which can affect astronaut health, including immune system function. At around 100 kilometers, the atmosphere produces an airglow, a faint light from ionized oxygen and nitrogen, visible from orbit during night. The Sun drives much of Earth's space environment through its radiation, solar wind, and 11-year activity cycle. Solar variations can change atmospheric density, which affects satellite orbits. Spacecraft also absorb solar radiation and re-emit heat depending on their material properties, with temperature balance explained by the Stefan-Boltzmann law. Gravity decreases with altitude and defines the gravitational well around Earth. Escape velocity from Earth's surface is about 11.2 km per second, while circular orbital velocity is 7.9 km per second. Orbital shapes depend on energy, ranging from circular to elliptical, parabolic, or hyperbolic. Spacecraft change orbits through maneuvers applying delta V, velocity change. A Hohmann transfer moves between two circular orbits efficiently, while plane changes adjust orbital inclination. Special orbits like geostationary keep satellites fixed over one point on Earth. Rendezvous missions bring two spacecraft together, such as the ISS and a visiting vehicle. This requires careful orbital matching, burns for approach, and precise control in 6 degrees of freedom. Tools like star trackers, radar, and optical sights assist astronauts in completing docking or capture operations safely. Conclusions. At about 100 kilometers above Earth, a faint natural light called Airglow surrounds the planet. It is caused by atmospheric gases like oxygen and nitrogen releasing energy after being excited by sunlight, and it is especially visible from space when the Moon is above the horizon. In space travel, changing a spacecraft's orbit requires carefully applying a change in velocity, known as delta V. This maneuver changes the spacecraft's path and energy. A widely used method for moving between two circular orbits is the Hohmann transfer. In this technique, the spacecraft starts in a circular orbit and, at a specific point, receives a burst of speed in the direction it is already moving. This extra velocity increases its kinetic energy, changing the orbit into an elongated, elliptical shape with a larger average distance from Earth, semi-major axis, than before. Once the spacecraft reaches the farthest point of this new elliptical path, a second delta V can make the orbit circular again at the new altitude. This process is energy efficient and is often used for missions such as moving satellites to higher operational orbits. In many cases, the starting point is not in orbit but on the ground. Here, the chaser spacecraft is launched toward a target spacecraft already in orbit. The chaser performs precise delta-V maneuvers to match the target's orbit and position for rendezvous. This is a critical step for missions such as crew docking with the International Space Station, satellite servicing, or cargo delivery in space. By combining the understanding of atmospheric effects like airglow with precise orbital mechanics, space missions can navigate efficiently and conduct complex operations far above Earth's surface. This important article is authored by the following scientists. Thank you for watching this video. Please subscribe to our channel BP International to watch more videos in the fields of science, technology and medicine.